Hello. Okay, so I believe we're going through complex numbers. Someone is asking, how do I record? Don't worry, we are doing the recording for you. So that yeah, we'll upload it on YouTube later. So we are doing the recording for you. So no need to worry. Okay. And we'll upload it on YouTube. So I hope you are fine with that. So we're going to start with our algebra. Okay. I believe we're doing complex numbers. Okay, so I'm going to put a few questions on the board so that we solve it and go through it and see how we can be able to find solutions to these complex number problems. Okay, so I'm going to put a few questions down. It's not really anything much. So the first one, I hope you, everything is clear, especially you can do being in my class. In the class, and I have you guys to solve. So I'm sure we are not having much problems of math. After the 5 minutes, we will go through the so for the first time is I'll try my best. Okay, so I'm sure most of you, some of you who have joining from home. So this is the first time you are doing the tutorial. So I would ask that you try and follow along, okay? Because we are doing a little bit of revision. Okay, this revision is for the sake of those who have not been here. Yeah, so I'm just putting these questions on the board, and then I'm giving us a few minutes to solve it, and then when we come back, when I come back, we'll see how we'll be able to deal with these questions. Okay, and then we move on to our next thing. Thank you very much. If you have any question or any comment, please type in the comment section, okay? Please type in the comment section. Thank you very much. Yeah, please, if anyone is done, if you are done, you can just type, oh, I'm done in the comment section. Yeah. Hello. I hope most of you are done at least with the first one. Okay. Someone is asking if this for only engineering students. Primarily is for it's for engineering students. But then if you also do algebra, you can join because this is basically the same thing that you'll be doing. Yes. Thank you. Hello. Did you hear what? Okay, I said primarily is for algebra, is for engineering students, this tutorial. But if you are doing algebra, you can join in. So I hope most of you are done at least with the first one. So we are come to solve the first one. Okay. So we are come to solve the first one, okay? Those who can hear me, I hope you can hear me right now. But you can write the questions down. I'm giving you 1 minute to do that, please. All right. Hello. I hope you can all hear me now. We are going to start with the first question. So, in solving this question, there are a lot of ways we can solve this. Okay, there are a lot of ways we can solve this. So we'll start with the easy ones. We'll start with any of the ways. Let's just start with. So let's start with the first way. Okay, the one that we all know. So in this question, we can see that the denominator is squared and the numerator is just a normal complex number. Okay. So first of all, let's deal with the denominator and then we use the normal way of dividing complex numbers to solve. I hope you are clear with this. So let's start with the denominator. So we have 1 minus 3i squared. And you can simply do it the usual 1 minus 3i multiplying 1 minus 3i. Okay. I hope you get this one. 1 minus 3i multiplying 1 minus 3i. Okay. So in this case, we are going to just multiply through. Okay. So we have 1 multiplying 1 giving us 1. We have 1 multiplying minus 3i giving us minus 3i. We have minus 3i multiplying 1. That will give us minus 3i again. And then we have minus 3i multiplying minus 3i. That will give us. So we see in this case that, okay, let me. So the minus will go and become plus 9, but be I squared, okay. And we know that I is the square root of negative 1. So in that case, instead of writing I squared, we are going to write minus 9, okay. So if we solve it, if we write it, we get for the numerator, sorry about that, we have minus 8, okay, because 1 minus 9 is minus 8. And then we have minus 6i. And then for the numerator here, we have 1 plus 3i. Okay. So this is the new complex number that we have. And now it has become easier to solve because we have a denominator that we know of. So all we are going to do is we are going to multiply by its what? Complex conjugate. Okay, the complex conjugate. Someone is saying they can't hear. Please, can you hear me now? Can you hear me now, please? If you can hear me, give me a reaction or tell me in the chat. Okay. So for the I squared, okay, we know that I is what? The square root of minus 1. I being the notation we use when we are dealing with complex numbers. So complex numbers are just numbers which are multiplied by the square root of negative 1, which is I, okay. So when we say I squared is just the square root of minus 1 what? Squared. I hope you get it. So it's the square root of minus 1 all squared, which is minus 1. That is why when we got 9i squared, okay, because I squared is the square root of minus 1 all squared, that's why I squared is also equal to minus 1. I hope you understand what I'm saying. Yes, exactly as Galaxy S10 told us in the chat. I squared is equal to minus 1. So all I did was I substituted I squared with minus 1, and then I was able to get minus 9. Yeah. So right now I've been able to get my denominator. So let me clean all this. I hope it's clear to you why I had a minus 1. Okay. I hope it's very clear to you why I had a minus 1. If it's not clear, someone should say something. If you don't understand, okay, it seems that you all understand this part. So continue with the function, okay, with the complex number we have here. We have the denominator that we know, and we have the numerator too that we know. So I'll just go ahead to multiply both sides, multiply by the complex conjugate, okay, of the complex number. So we have the complex conjugate to be minus 8 plus 6i. Then we have minus 8 plus 6i. So we are going to do more multiplication over here. So that's why it's important that you understand what you are doing. Okay. So let me erase the denominator part. I hope you've all taken note of what is happening. Okay, thank you. So I'm going to clean the denominator part and then we continue with that. So we are come to multiply. We know that if we multiply a number, okay, by its complex conjugate, it's a very, very nice way of simplifying. Let's try and see. Okay, we have minus 8 minus 6i. Okay, and then we have minus 8 plus 6i. Don't worry, this revision we are doing it for the sake of those who weren't here. Okay, those who were at home and haven't been able to do the tutorials. So when we simplify this, we have 8 times 8, that's positive 64, okay. And then we have 8 times 6, that's 48. And because we have, so we are doing it minus 8 times minus 8. Minus 8 times minus 8 will give us 64, okay, positive 64. Then we have let me do it the other way. We have minus 8 times positive 6. Okay, that will give us minus, let me do this. We get this. Like anywhere you see I, you just negate. That's how we find complexity. The imaginary part of this equation is okay. And then I hope you know the complex conjugate is just the it's just the same complex number, but just that we change the sign on the imaginary part. So we change the sign on the imaginary part to get its complex conjugate. Okay. You see why it's called a complex conjugate after we do this multiplication. So if we multiply minus 6 by minus 8, okay, we are going to get positive 48i. So let me write that down. And then we have minus 6 times positive minus 6i times positive 6i. That will give us minus 36i squared. Okay. Now we know what I squared is already. I squared is what? Minus 1. So we are going to substitute the I squared and we are going to get in the end. So when I move the I squared and I substitute, instead of minus, it's going to be plus now. So plus 36. Okay, and there's no I. So if we multiply two complex conjugates, all we're going to get is a real number, because you can see from here that here's minus 48i, and then here's plus 48i. And so if I add them together, they're going to cancel each other out. So let me erase it. So this goes with this. And so we get 64 plus 36. And this is a beautiful kind of solution, because if you look at this, let me write it well. So if you look at it, if we multiply two complex conjugates, all we get is the squares of their imaginary and real parts adding up. Okay, so if I have a plus bi multiplying a minus bi, what I get is a squared plus b squared. Okay, a squared plus b squared. I hope you understand. If you don't understand anything so far, please say it in the chat. The left hand side, the right hand. Okay, so we can move on now. So let me erase this. On the left hand side, the real part is a plus b. And on the right hand side, the real part is 5. So let me erase this one. It's equal to 5. So from this equation, we can get a. So right now, I can just say it's equal. So we know our denominator already. 64 plus 36, or 8 squared plus 6 squared. That's how you can do it. And it's like, because it's a squared, it doesn't matter the sign. Okay, it doesn't matter the sign on the 8 or the sign on the 6. It doesn't matter the sign. At the end of the day, you just get two positive numbers, okay, adding up. So 64 plus 36, okay, that's when two complex conjugates multiply. So we are going to multiply the top, okay, and then it's not too hard to multiply the top. So we have 1 times minus 8, that will give us minus 8. We have 1 times 6i, that will give us 6i. We have 3 times minus 3i times minus 8. That will give us minus 24i. And then we have 3i times 6i. That will give us 18i squared. You can be lazy small, and then instead of writing I squared, you will know that, oh, this is I squared, so I'll just make it negative. But it's too hard to be like thinking about it every time, and you might forget. That's why it's safe to do everything normally. And then you know that, oh, this side is I squared, so we are just going to make it negative. Okay. So we are going to make it negative. So remove the I squared from here. Then we're going to make it. Sorry. So this is the solution to the first equation. We're going to make it negative. So we are just going to simplify this. So for the real part, we have minus 18 minus 8. So that's minus 26. And then we have 6i minus 24i. That will give us minus 8. Sorry about that. That will give us minus 18. Sorry. I all over, and 64 plus 36 is just 100. I hope you understand. Okay, and you don't leave your answer like this. You of course you simplify. You get 26 minus 26 over 100 minus 18 over 100, and then we do the division. Okay, so please try the next question I'll be back with you soon. Okay, so we are come to try the next question. I hope you all understand what is happening. Okay. And please, I squared is -1. I repeat, I squared is -1 because I is the square root of -1. So if we are finding the square of a square root, all we do is remove the square root. Okay. So if we remove the square root, we'll be having -1 as I squared. Thank you very much. So I'm come to put the next question on the board so that we all see and then we go through. For those who just joined, please try and follow through what we are doing so that you understand. In the next question, I'll repeat a few things that we did here so that you understand what is going on. I'm coming to take question before I get so for the first question, after question stage, find all complex numbers. And don't worry, all the questions we do here will be posted in the main algebra group. Okay, so yeah, and I'll advise you, please reduce your answers. Some lecturers won't mind you if you give half answers or unsimplified answers because they have a feeling that you have to simplify it, okay, instead of leaving it for them to simplify. So I would just advise you, if you can simplify your question, please simplify it, okay. So the next question is 1 plus I to the power 1/3. You need to know what z by. And from the previous question, we knew that z bar is the complex number. So I hope you've all started writing your solutions to it. I'm giving you 1 minute to sort yourselves out, and then we go on to what is going to happen. So let's name this question 1. Question 1, that's z is multiplying z back. Some of you guys want the question. I'll make the question and then I'll do it. Okay. Please show the steps. Show the steps. Okay, when you are solving these questions, try and just show steps. Okay. Well, it's up to you to to know the steps you should show, but you show the important steps. The calculations are not really necessary, like showing how you calculated is not necessary, but show the steps. For example, if you're solving, okay, if we were solving the previous example, because I've cleaned it, you might not see what I'm talking about. But then you doing this, I'll tell you, like you have to tell the lecturer that you know what you are doing. So you put the steps that are necessary over there. So for example, addition, subtraction, those things are not necessary. But then the important steps are the ones that you have to put down. So let's go through this. Okay. So 1 plus I is the power 1/3. So in this case, we are finding the nth root of a complex number. Okay, and this one is the cube root. Okay, and because it's the nth root of a complex number, so we know from basic math that if you are finding the square root of a number, okay, I mean the square root, yeah, let me take it this way. If you are solving a quadratic equation, okay, like a quadratic equation is in the form x squared plus ax squared plus bx plus c. This is a quadratic equation. We expect two solutions. We have two solutions. Okay. And then if we have a linear equation, that's ax plus b. Yeah. Sorry. So if we have ax plus b, we expect one solution. Sorry about the annotation. We expect one solution. We expect one solution. Okay. So you can see that depending on the power of x, it determines the number of solutions that we expect. So a cubic equation will expect 3 solutions. Okay. So it's the same for finding the root of a number. Okay. So in finding the nth root of a number, we expect n solutions. Let me go there. If we are expecting, let's say, 1 plus I raised to the power 1 over 10, that means that we are expecting 10 solutions. Even if you have 1 to the power 1 over 1 over 10, we expect 10 solutions. And trust me, the only way you can get this is through complex numbers. Using real numbers, okay, real numbers, we only have one solution to this, which is 1, okay. But if you add the imaginary side, okay, we get 9 other different solutions to add to this. I hope you understand what I'm saying. So if it's 1 to the power 1 over 3, we expect 3 solutions. Although in the real world, we only know that if we find any root of 1 is 1, okay. But then in the complex number world, that's not what happens. So let's see how we can solve this. Okay. Let me erase. So let me go back to the original question. And then after expanding all this, we had Z plus Z plus someone is asking me to repeat. Okay. What I was saying is that if we are finding the nth root of a complex number, what we expect to see is that we expect n different solutions. In this case, we expect n different solutions. In this case, 3 different solutions. Okay. And so let's try and solve this and see what we are going to get.
So this is equation 1. And then the other part of the question was getting at A plus.
Okay, so now if you have a complex number, Z, okay, if you have a complex number, Z, and we are expressing Z as a complex number, we can actually write A plus BI. That is in this linear form. And according to this, it means that we can also write it in its polar form. Okay. We all know that if we have a complex number, we can plot it on what we call the complex plane, where the horizontal axis is a real part, and then the vertical axis is our imaginary part. I hope you can visualize what is going on over here. Okay. I hope you can visualize what is going on here. So, okay. So let me mark it out. Let's say 1, 2, 3. Minus 1, minus 2, minus 3. Okay, so we have this. So we have this. Clearly, my annotation is getting a little bit messy, but I hope you can see. I hope you can see what's happening. Okay. So now, what we are saying is that the real part is when we hadn't done complex numbers, everything we're doing was on the real plane. So any number that we know is a number on the horizontal axis. So like 1, we know 2, we know 3, we know 4, we know 5, we know 100, we know up to positive infinity, and we know up to negative infinity, and that's the real part. Okay, so we also have what we call the imaginary plane. Okay, and that's the imaginary part. So the value on the imaginary line is in this case B. So we can have the same thing here, 1, 2, 3. But then you know that it's multiplied by I. Okay, minus 1, minus 2, minus 3. You know that the imaginary part is multiplied by I, and that's is something that you have to do.
Solving this equation in the calculator gives us A to be 4
Okay.
or 3.
And so we are going to see something. So for example, 1 plus I, okay. 1 plus I is just this. So let's say Z was 1 plus I. Okay, let's say like that. Z is 1 plus I. So if Z is 1 plus I, that means that our A or our real part is 1. And our imaginary part is also 1. But because it's multiplied by I, we call it I. Or we can't just say 1I. It's to be sounding weird. So that's why we just say I. So we have 1 on the real, 1 on the imaginary, which gives us a point, let's say, over here. Wait, I'm coming. Let me draw it well.
complex number z is of the form a.
So let's say that's the point we have.
So when a.
So this is the point. So if we draw a line from the center to here,
7 minus
okay,
7 minus 4.
this is our complex number. Complex number is actually the point over here. So I'll call it z. And how do we know that point? And that's the reason why we have different ways of writing complex numbers. So in this Cartesian form, okay, or linear form, we have a plus bi, okay. So we have the real axis and imaginary axis. So we just move by 1 unit on the real axis and move by 1 unit on the imaginary axis, and we have this point here, z. Okay, I hope you understand how we got the z. And so in the same way, we have a polar form of writing complex numbers. Okay, we have a polar form of writing complex numbers, and we use the angle it forms with the real axis. Okay, we call it theta. Yeah, so because we call it theta, we express, instead of expressing it in Cartesian form like this, we express it in polar form, where we have the magnitude, I'll call it, it's called the modulus. Okay. Yeah, it's called the modulus of a complex number. So the modulus is actually this length, the length of this, okay, the length of the z from the origin. So from the origin to our z, we have this. It's called the modulus of z, okay. And I'll tell you how we can get it, okay. And then we have, so because it's a polar form, okay, in polar form you always see cos theta, okay, for the horizontal part, okay. Because it's taken from respect to the real axis, we have cos theta first, being the real part, and then sin theta, because sin theta is the imaginary part. I'm sorry for my screen, okay. Let me. So we have this. Don't worry, it will get better right now. So I'm working on how I'll make this work. So we have cos. So this is how we express complex numbers in polar form. But all we need to know is
1. So that z minus z 1 all over z plus z minus 1 all over z.
all we need to know is how we express the complex number as a, how do you call it? How we express this rectangular form in polar form. So the two things that we don't know here is theta and z. So we have to work on a way of finding theta and finding z. Okay, the modulus of the complex number. Okay, so let me erase all of this, and then we come to how we can do it and how we relate to finding the root of a complex number. Thank you. I'm coming. Let me erase all of this stuff. Okay, so let's go back to our question. So our question is B is our question B, z is equal to 1 is it 1 minus, yeah, 1 minus,
All meaning the same thing. So the actual value of z
1 plus I to the power 1 over 3. So we are going to complete how to find the modulus. So finding the modulus of z is not the hardest thing. It's actually the easiest thing to do, because the modulus of z is just the square root of the real part plus the imaginary part, or the imaginary part squared. So we're going to square the real part and we add it to the imaginary part. So we have 1 squared plus another 1 squared. This time we don't add the I. We just need the imaginary part, or the part that's on the imaginary plane. And the imaginary plane, we didn't write I on it, so you understand what I'm talking about. So if we had A plus BI, and we are finding the modulus. I'm sorry for this. If we have A plus BI, and we are finding the modulus, we just have square root of A squared plus B squared. Hey, I'm sorry, my marker is no. A squared plus B squared. I hope it's better now. Okay, so we have this to be the modulus. Let's call this W. So the modulus of W is A squared plus B squared. Note that we don't add the I to it when we are doing this. Okay, so our modulus of this is just I squared. That's 1 squared plus 1 squared. Sorry about the I squared. There's no I squared. 1 squared. And because 1 I, we say 1 squared. Okay, don't add the I when you're finding the modulus. Okay. So we've been able to find the modulus. Let me not erase it. And now it's up to us to find the angle. This angle too is not the hardest thing to find. Okay. The angle is just the tan inverse, okay, of the imaginary part over the real part. Okay. But then it's not as simple as this. You understand in a bit. So naturally, let me tell you how they concluded on this. So if we have the plane, I have a complex number, okay, z on it, okay, and we draw a line. This is theta, okay, the angle it forms with the real plane is called theta. And now, from what we know, if I'm going to divide it, okay, this is the x part, or the imaginary part, and then this is the real part. Sorry, this is the y part, or the imaginary part, and this is the real part, or the x part. Let me. So we have z, y, and zx, or the imaginary part. That's the vertical. This is the imaginary, and then this is the real, or the zx, because it's zero on the horizontal plane. So that's our real part, zx. So what we are saying is that, okay, and we know that if you are finding angles or from trigonometry, okay, from trigonometry, what is tan theta? Tan theta is just the opposite. Yeah. Please, those who have raised their hands, please type your question in the chat. Okay. Please type your question in the chat. Could I go over? Okay, starting from when? Starting from where? Is it about the imaginary and then complex plane thing? Or is further than that? Okay, the imaginary and then the complex plane. So let's go over this. So I'm going to remove the question for now. And then we're just going to deal with imaginary and complex plane. So these are plane. These are real. And these are imaginary. It looks like what we've been doing in our graph books since JHS and SHS. It looks like X and Y, okay? But this time, instead of X and Y, we are writing real parts and imaginary parts. Okay, so if I have a point here called A, and a point here called B.
When I bring you have A minus 1. Since A and 1 are real, I do it to one side. Plus,
if you have a number called A on the real plane and another number on the imaginary plane called B, then the point of intersection is a complex number. So this is a Z. Okay. Now the thing is, if a number had no imaginary part, or okay, we can say, let's call this theta, the angle between the horizontal plane, okay, or the X, or the real part, and the line of the complex number is called theta. We just call it theta, or it's called the argument, okay, the argument of the complex number. Don't worry, we'll come there. We are not yet there. Okay, we are just looking at how real numbers and complex numbers all fit into this complex plane. Okay, the two of them combined is called the complex plane. Now for the real part, okay, we have A. So if a number had only A, okay, so Z is equal to A, we call it a real number, okay, because it has no imaginary part. So the B is 0, so A plus 0I, we call it a real number, okay. So we are plotting real numbers. Because the imaginary side is 0, all the numbers fall on the line, exactly on the line of the real axis. So they fall on this line. Okay. I hope you understand that. And we also know that if a number only had the imaginary part, okay, if the number only had the imaginary part, so Z is equal to 0 plus BI, that means that this number is a purely imaginary number. Okay, it's a purely imaginary number. So all the numbers will fall on the line, or the Y, or the imaginary plane line. Okay, so we have this. So all the numbers fall here because the real part is what? 0. So it has no real part. It only has the complex part. So it will fall on that line, exactly on the line. I hope you understand what I'm saying. If you don't understand this part, please tell me right now. Okay, thank you. So we'll go back a little bit. So now we're going to look at this carefully. So if we have a complex number, that's a normal complex number. So we have real numbers, imaginary numbers, complex numbers. Complex numbers is just a number that has both the real part and the imaginary part. So if I am doing a complex number, I'll say it's A plus B I. Okay, and that's what makes it a complex number, because it has both real and imaginary parts. Okay. And now, this is the normal convention of writing complex numbers because it looks like a rectangular. It looks rectangular in nature because we have A to be a number on the real part and B to be a number on the complex part. So it's like X and Y. Okay. So A and B is our X and Y. Do you get it? I hope you get it. B is our Y and A is our X. Although that's not technically true, but you can relate it because it's the same concept. Okay. So the I is what makes it an imaginary number. Okay, if it was just A plus B, then you can just add it together and to become it will still be a real number. But because of the I, we can't add the complex part to the real part directly. That's why the complex part should always be multiplied by I. Okay, because when it's multiplied by I, we can be able to say, oh, okay, because multiplied by I, then fine. Everything is a complex number. Okay, I hope you understand that. Okay, and so because a complex number is expressed in the form A plus BI, which is the normal form that we write it, or the rectangular form, there's another form that we write it. That's the polar form. Okay, so our polar form is such that instead of using A and B, okay, to denote it, we use the length of the complex number, okay, which is called the modulus, okay. So in real number system, we call it absolute value. It's the same as the modulus, okay. We call it the absolute value of a real number. But in the complex number system, we call it the modulus of a complex number. And the modulus of a complex number is just the length of the complex number. And if you are using normal trigonometry, or if you look at this as a right angle triangle and whatever, you can conclude that this, okay, the hypotenuse, okay, of any right angle triangle, okay, squared is equal to the square of the opposite side and then the adjacent side. So we have A squared plus B squared. I hope you get this part. I'm sure you. So this is how we find the modulus of a complex number. We just square the real part and add the square of the imaginary part. And no, that's equal to the modulus squared. So if we want to find the modulus, okay, all we have to do is find the square roots of it. That's so square root of A squared plus B squared. I hope you understand. Yeah. So in this case, we are through with how to find the modulus of a complex number. And now the argument is where the issue is. Okay, I'm going to say some things important, so please pay attention as much as you can. Okay, so let me get rid of, okay, let me keep this one. Okay, there we go. So we are finding the argument or the angle, okay, that makes the number mix with the complex number. Now, if we still use our trigonometry, our normal trigonometry, we can see that let me see, you can see that tan theta, okay, will be what? The imaginary side B over the real side A. You can see that we are not using I, okay, when we are looking at argument and when we are looking at modulus. Make sure you don't add I. I beg you. I beg you. Okay. And so we can just say that theta is what? Tan inverse of this B over A. We are not wrong, but we are not right. We are not wrong, but we are not right. Because there's something extra that we have to do. Note, there's something extra that we have to do. So please, let's just go through this quickly and then we can go to our question. Okay, let me go back here. It's true that tan theta is B over A, but then let me write the 4 situations you can get where you have a complex number. So you have this situation, so I'll call it A. Situation A. Where else should I write it? And then we have, let me write it under situation B. Then we have situation C. And then we have situation D. I hope you get this. We have situation A, B, C, D. And I hope you can. Yeah. Tan inverse is the same as arctan. If for those who don't know, tan inverse is the same as arctan. So for these 4 situations, it's actually it's quite simple to know what kind of situation it is. So in this first case, okay, the real part is positive and the imaginary part is still positive. And so we can use the normal, the modulus, the argument is arctan. Okay, so in this one we can use the normal tan inverse of B over A. So that's when both of them are positive. So if I have a complex number Z, sorry about that. If I have a complex number Z is equal to 2 plus 3i, and we still find the argument, okay, or find the argument, the principal argument, or whatever, however they will put it. All you should know is that because both of them are positive, it's just the tan inverse of the real and the imaginary part. And remember, it's in your modulus. You can decide to either do it in radians or do it in degrees, but you should know what you are doing. Okay, if you are using radians, fine. If you are using degrees, fine. But you should know what you are doing. Okay, I hope you understand. You can decide to do it in either radians or degrees. There's no, if it's degrees, you have to put a degree sign or something over there. If it's radians, yeah, maybe make it a multiple of pi, or I don't know how. But just make sure you know what you're doing. Okay. So let me just continue with this. Okay. Fast. We are behind schedule. Okay, so let me. So today is like mostly recap. So I'm sorry for those who are way ahead of this. But it's good to come back so that you can revise what you've done, so that you won't forget. So please, let's follow along. So in this case, the real part is negative, but the imaginary part is positive. Okay. Now take note. Take note of something. The angle, the angle that the arctan gives you, or the tan inverse gives you, is the angle with respect to the horizontal. Is the angle with respect to the horizontal, okay? So we have this angle theta. Okay. So when you find the arctan, you found the angle, yes, you found the angle, but then that's not the angle we are looking for. The angle we are looking for starts from the positive, okay, to the how do you call it? To the line. Okay. It starts from the positive of the axis, okay, of the real axis to where our line is. Okay. So in a case where you have the real part to be negative, so like z is equal to minus 8 plus 3i. So real part is negative, imaginary part is positive. You should know that if you find the argument, if you find the tan inverse, okay, it won't give you the angle you are looking for most of the time if you just put it in straight. So here is how you deal with that, and it will apply to all the things you're doing that depends on maybe graph work or maybe later when you're doing if you're doing basic mech, and then if you're doing all those other courses that require this, even applied later, you might have to know how to get your angle right. Okay, how to get your angle right. So in this case, the case where imaginary is positive and real is negative. Okay, let me erase this. Here's what you do. Now, what you do is that you find the tan inverse. Okay, first. And note, your B and your A should all be positive. Okay, your B and your A should all be positive. Even if one is negative, just make it positive. Okay, sorry about that. Just make it positive. Make sure you are able to get your real and your imaginary parts. So, for example, if you are doing this example, 8 minus 3, minus 8 plus 3i. Okay, minus 8 plus 3i. If you are doing the tan inverse part, so sorry about this. You find the tan inverse of 8 over 3, not negative 8 over 3. There's a reason why. Okay, so that your calculator will give you the acute angle. Sorry about that. It was a technical glitch. Okay. Please ask those who left to join. Okay, we are coming. We are come to continue. So I'm sorry for that. It was a technical glitch. We'll continue from here. So as I was saying, there are 4 instances, okay, where imaginary and real are positive. Real is negative, but imaginary is positive. And then we also have the case where both are negative, so negative, negative. And we also have the case where um, real is positive, but imaginary is negative. Okay. So we have these four different lines. Okay. And I told you that for this first one, okay, if you are finding the angle, it's not too hard. I hope you can all hear me. I don't know. They're not talking French. They're not talking well. Yeah. So what we are talking about is don't Hello. So we're in Ghana, so the unexpected happens. Yeah, the lights just went off, but we are back online. Yeah, so I hope you can forgive us for this one. Okay, yo, please call the others to come online. We are back online. Okay. Let me get back to where I was. Fast, so that. Oh, we are in Ghana. We are in Ghana. Oh, the system. So let's continue from where we were. We left off. Okay. I hope you can all still see. Um, okay, so we have this one. Um, we can, okay, we have minus minus. Then so as I said, okay, I hope those who were inside are joining back. Okay, sorry for that. Okay, we have for the real part, we just have our theta to be for the positive. So we have tan inverse of B over A. Sorry, where B is the imaginary part, A is the real part. So let me write it here. B is imaginary. Okay, A is real. Okay. I hope you all get this part. And so we also have for this part, this is the second one where we have B to be positive, but A is negative. Okay. I told you that we take angles from the positive real axis. Okay. So in this case, the angle will be here. So all we have to do is you have to know okay, if you are working in degrees, fine. If you are working in radians too, please can you all hear me? Please can you all hear me? If you can hear me, please type in the comment section before I continue. Please, if you can't hear me, please say it. Okay, so we are about to continue. We are about to continue. We're about to continue now. All right. So what I was saying was, so for the normal positive, all we have here is we have b plus a. Okay, that's the normal tan inverse. Sorry, tan inverse of b over a. Now for this one, I told you we take the angle from the positive x-axis. So in this case, we can see that we can get, so when the real is negative and the imaginary is positive, you can see that, so in this case, okay, we can get our theta, okay, to be a certain angle, that's 180 degrees, minus the acute angle. Let me write it down so you can, so we have a theta to be a certain, that's 180 degrees, minus, so 180 degrees is the full thing that's going from here all the way to here. I hope you understand that one. Minus the acute angle over here, okay, minus that acute angle, I'll just call it alpha. Okay, and how do we get that acute angle? That acute angle is just the tan inverse, as we already know over here, of b over a. But then you have to make sure b and a are positive. So I'll just put absolute value over here. Okay, so that you will know. Okay, make sure your a and b are positive so that you get an acute angle, and then you subtract 180 from it. If you are working in radians, okay, this one won't be 180. Okay, it will be pi. Okay. Okay, so try and Okay, so we are continuing. I understand your concern. It wasn't pause. I had to go and deal with something. Okay, I'm sorry. So I come to continue this one. Now we have when both of them are negative. Can you hear me? When both of them are negative, and when all of them are negative, what we have here is that theta is now we have 180 degrees. We have 180 degrees, okay, 180 degrees already, or pi radians. So 180 degrees is equal to pi radians, okay. So you can either use 180 degrees or you can use pi. If you are working in degrees, you use 180. If you are working in radians, you use pi. Okay.
One guy you're meeting was like, all we are talking about, not
Yes. So can you all hear me? Can you all hear me? Yeah. If you can hear me, please say it in the chat. Okay. So at this point, we have 180 degrees of pi, and then we have, so we already have 180 degrees. Now we are going to add an acute angle to it, the same alpha. So all we have here is, now this time, instead of minus, we have 180 or pi. Don't, let me put it in brackets instead of slash, otherwise it will make it confusing, okay? Let me use the brackets for it, okay? So 180 degrees or pi, okay? 180 degrees or pi. And we, instead of minus, we do plus tan inverse, sorry, this tan inverse of, now you still have to use the absolute value, okay? Make sure they are positive. No negative, because we just need the acute angle, like how we found the first one. The first one, they're both positive, that's why we don't need the absolute value. But since we are using the absolute value, then it means that someone said you don't think anyone will use pi. Sure, people are angry, they will use pi. Okay, so we have the next one. That is when real axis is positive and imaginary axis is negative. And that one, you can see that we have 360 degrees minus the acute angle. I hope you can see it. I know we are going fast a little bit, but then, so you have 360 degrees or 2 pi if you're using radians. I want you to see all of it so that you can understand what's happening. Okay. 360 degrees or 2 pi plus, minus, this time it will be minus the tan inverse. Okay, I know it's small, but bear with me. Tan inverse of the absolute value of b over a. Okay. So these are all the ways we use to find our angle. Okay, so the third one, you're saying why shouldn't it be 270? That's what someone is asking. Well, not in this case, okay. I would say no, because we know that the angle we find, that acute angle, is from the horizontal axis, okay. The horizontal axis, okay. This is the horizontal axis. To me, it's the line. So if the horizontal axis starts here, this will be the angle, not this. So we can't use 270. If we use 270, what are we going to subtract from 270? We don't know this angle. Okay, so we obviously do the 180 and then we add the acute angle because we are starting from the horizontal axis to meet the line. Okay, the reason why we use 180 degrees for the second one is that we know this acute angle, okay, that's this. So we know that, oh, 180 is here. So if I subtract the acute angle from 180, I'll get the angle that I expect. Okay, so I hope you get that one. And for the first one, is pretty straightforward. So I hope you understand how we get our angles. Yeah, so this is quite extensive, but then it will show you why the angles are how we get them. Okay, so you don't just do the first one and think you're fine. You have to watch and know whether, okay, it's one positive and one negative or both negative, so that you can see what you do. I hope you all understand this one. If you understand, give me a thumbs up. Okay, so we're going to continue with the question. Let me just finish this question. Okay, it's almost 12. It's almost 12, so let me just finish this question with you. All right. Okay, so here we go. We have a question to be 1 plus I to the power 1 over 3. Okay. And now we know how we find our modulus, and we know how we find our argument. And note that the argument that I talked to you about, we normally call it the principal argument. Okay, I'll explain why it's called the principal argument later. But just know that, okay, that's the principal argument. So yes, that's how everything goes. So let's try and solve it for this question. Let's say z is equal to 1 plus I. Okay, so we have the modulus of z is what? One square root of what? 1 squared plus 1 squared. Okay, and square root of 1 squared plus 1 squared is obviously the square root of 2. So now we have so we have this. So we want to know our argument. Okay, we want to know our argument. So we can see that both of them are positive. I is positive. This is 1 I, so we know that okay, it's 1 I, so I is positive. And we have the imaginary part positive, and then the real part is 1, and 1 is also positive. So we're going to combine these two, and then we're going to be able to get what we have. Okay, so once you know that angle is theta, okay, so and because both are positive, our principal argument will just be tan inverse of 1 over 1. So tan inverse of 1 over 1 is either if you're using normal angles, it will be 45 degrees, okay, or yeah, so 45 degrees. Or if you are using radians, okay, if you're using radians, it's going to be pi over 4. Okay, pi over 4 is 45 degrees. So I hope you understand now. For this 1 plus I, we'll be able to get our modulus, and then we'll be able to get our angles. Okay, so now let's continue. Let's continue with this. Okay. So right now, since we are able to find our principal argument and our modulus, we are going to the polar form of writing complex numbers. So complex numbers are can be written in the polar form. So in the rectangular form, z is equal to, let me write it well. Z is equal to a plus bi. And in the polar form, okay, so this is rectangular. So in the polar form, you can write it as modulus of z. Okay. The first thing writes the modulus of z times cos theta plus I sine theta. So theta, you should know, is the principal argument, or the theta we find with our values. Okay. I hope you can all hear me. Okay. I hope you can all hear me. Now modulus for 1 plus I, our modulus was root 2. And then the argument was 45 degrees, or pi on 4. Okay. Pi on 4 radians. So a plus bi, someone is asking, why is a plus bi expressed in polar form? Why is a plus bi expressed in the polar form? So the reason for, why is a plus bi called rectangular in the first place? Rectangular because it's exactly like the rectangular coordinate system that we've been using, where if this is x and this is y, any points can be expressed as x comma y. You get it? So in this case, a plus bi is a comma b. Okay, in the imaginary and the real plane. If I draw my imaginary and my real, this is if I want a point to be a comma b. Okay, so that's why it's called rectangular. You get it? I hope you understand that. And so let me get rid of this. Any, any other? Okay, so you understand. Okay, thank you. So when we're writing in polar form, okay, writing in polar form is just like and some of you have read ahead and been able to do the polar coordinate system, but then if you don't know about it, okay, if we have, so these are complex numbers z, okay, these are imaginary, these are real. So the polar form just says that find the length of this. Okay, find the length of this. Simple. So the length of this is called the modulus of z. Okay, and that's how we normally find the modulus. Okay, and then after, what we do is we find the argument or the angle, and then we write it in this form. Okay, well, so the cos theta is the real. So if we expand, we have z cos theta being our real parts, and then we have z, I'll just say I sine theta. It doesn't matter how you write it. The I can be anywhere, but make sure the lecturer knows that it's I. Okay, I hope you understand that one. So you can express in this form. So this is the real part, this is real, and this is the imaginary part. So, oh, this was very interesting. Okay, when they discovered this first, and De Morveau, or I don't know how they pronounce it, or De Morveau, okay, he made a theorem. Okay, he was sitting here somewhere, and then he decided to say that he decided to give us wahala with complex numbers. So let me write something after the polar form. Okay, so he just said that if something can be written in polar form, okay, there's another way we can write it. Okay, if something is written in polar form, then we can write it simply this way. Okay, with a natural log. Okay, e, the So I hope you are familiar with E or you've seen it somewhere. E comes from natural log. But then he says that if you can write something in polar form, okay, then you can write it as an exponent where the argument or theta is the exponent of E. Okay. I know it looks a little bit confusing, but then he just said that, oh, if you can write it this way, then you should be able to write it this way. And it makes our calculations easier. Okay, don't worry, they've proven it. Okay, they've proven it. Yeah, they've proven it. All right. I don't know what they used to prove it, but they've proven it. So take note, this is very important. If you can express a complex number like this, in this polar form like this, then it's possible or it's safe and it's right and it's feasible and it's important that you can write it in this way. Okay, you see the modulus, okay, multiplying e to the power theta I or I theta. Doesn't matter where you put the theta, but the lecturer must know that that's I. Okay, the reason is, okay, it helps us do some petty calculations like division. You can see that it will make division and multiplication of complex numbers easier. Okay, instead of doing one by one like the way we did in the rectangular. That is, if you have a plus b, I multiply by another a plus. Okay, let me do a plus ci. Then we have to multiply it multiple times. So a times a times c, b times a, b times c before we can simplify and get our answer. But if it's in this form, we just multiply this and this together. So, and then what happens is that we just have to deal with how this one multiplies and how this one divides. Okay, you've probably already done it in SHS. So if I have e exponent a and I multiply it by e exponent b, sorry about this. If I have e exponent a and I multiply by e exponent b, it just becomes e exponent what? A plus b. Okay, so you can see how easy it's going to make multiplication right now. Because if I have two complex numbers, all I have to do is multiply this with another of this, okay? And it will just be adding the exponents on the e. Don't worry, we'll go through examples on that, okay? And the next part is we also have division. In division, all we do is, I'm sure it's obvious to you by this time, if multiplication was adding the exponents, then division will obviously be subtracting the exponents, e exponent a minus b. So you can see how important the Morris theorem is and how important the changing from rectangular coordinates to polar to this form, the exponential form. All right, so let me erase this and then let's go into solving the actual question that we put there. That's 1 plus I to the power 1/3. Okay, I know it's getting a bit complex. If you have any questions, please put the questions down. Okay, it will be very important for us to be able to know the questions and be able to how do you call it, deal with or tackle the questions so that you understand it better. Please, this is the opportunity I get it, so please use it well. Okay, use the tutors, use us. Okay, thank you. So at this point in time, okay, now we have exponential form. Okay, we've been able to say that, okay, once you can express as a polar form, you can express it as an exponential form. So that's what I've been trying to get us for the past, for a very long time. Okay. And so we have, so if you say a complex number, okay, raised to the power 1/3, so the solution to this, if I say a complex number raised to the power 1/3, or a complex number raised to the power 1 over n, okay, has n solutions, okay, and let's say w is a solution to this equation, and let me write w. So if w is a solution or a result, if I say z to the power 1 over n is equal to w, that means that w is a root, okay, an nth root. Okay. Someone is asking that he doesn't understand the parts that you can use the exponential form for multiplication and division. Don't worry, I'll get it to you. I'll get it to you. I'll get to that part or that point right now. Okay. So right now, let's just finish with this question, and then when I'm done with this question, by the time I'm done with this question, you will understand how it's important for multiplication and division and all of that. Okay. Thank you. So we have z is 1 over n, okay. Z to the power 1 over n is equal to w. So this means that w is obviously a root, okay. W is a root, an nth root of z, okay. So if I say 4 to the power, okay, 4, 1, yeah, 4 raised to the power 1 over 2, or let's say the square root of 4 is 2. That the result I write is 2, right? Means that 2 is the square root of 4. 2 is the square root of 4. Okay. Do you understand what I'm saying? Okay. I hope you understand. So if I say a number raised to the power 1 over n is equal to w, that means that w is an nth root of z. Okay. Or if the n was 2, it would be z. W is the square root of z. If it was 3, w is a cube root, and so on and so forth. Okay. So let's just continue. And so if that's the case, if this is the case, I can see that z is equal to w to the power what? M. I hope you agree with me. I hope you agree with me on this one. If you agree with me, say I agree in the chat. One person should say I agree in the chat. So let's go. Okay. Please, if you can't hear me, please say it. Please say it. Okay, I can see a lot of you agree with me. So it means that some of you can hear me. Okay. So let's move on. Okay. Now, if this is the case, okay, we can then say that, okay, if this is the case, right? If the z to the power 1 over n is w, that means that w is an nth root. Okay, so w to the power n is equal to z. Okay, I hope that's fine with you people. So according to the theorem, okay, so I can say my w is a complex number. My w is a complex number. Okay. So since w is a complex number, we can write w. We can write w as a plus b I. Okay. That means that w to the power n is what? A plus b I to the power n. Okay. A plus b I to the power n. Having this in this form, it will be very hard because would I do the whole equation and simplify? It will be very, very complex because it's in the rectangular form. That is why we have to convert it to the polar form. And in the polar form, we have the magnitude of w, okay, times e to the power theta I. So this is what we raise to the power n. Okay, so theta is our principal argument from what we did earlier, and w is the modulus. I hope you understand where we are going to. Please, if you don't understand, please say it. Okay. Right now we are advancing on what we already know. So sorry for that. Sorry for the network problems. The light just came back. Okay. Yeah. Okay. So we are come to close right now. Okay. Yeah. Sorry for the difficulty. The light just came back, so it's quite something. Ghana we did. Okay. So let me just finish up with this. Okay. And I know we are behind. I'm behind. Okay. I just want those who weren't here to understand this thing. So we just move on. Sharp, 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 sharp. Don't worry. Based on this meeting, because this is our first online, okay, we'll use this and then we make the future experiences a lot better. I'm sure after this, there will be no. Yeah. So I'm sorry for the how do you call it, the glitches and all of that. Okay. So yes, at this point, I'm going to just say that we'll continue, okay, but go and revise because you're going to. Okay, someone is telling me to complete the question first. Okay, so yeah, we'll have this meeting. Okay, but we'll be ahead that time. I want you to revise that we'll go further and then we'll finish. We'll be done with complex numbers and we'll go into our vectors and then matrices and all of that. Okay, so this is just the first meeting. That's why things are a little bit rough. But then I assure you that after this meeting, okay, the rest of them there'll be little to no interruptions. Okay, so we are working on it constantly, and so let me just finish this with you, and then after that, we just so yeah, let me just finish this one with you, and then when we move on, the next meetings and all of that. So tell your friends. See, there will be no more interruptions. So please, let's just come around. Okay. So we have this. Our W is the modulus e to the power theta I. Okay. This is our root. Okay. Our root is a complex number. So all we have to know is what is our root. Okay. We want the nth root. Okay. So we know that um, the root to the power n is equal to z. Okay. The root to the power n is equal to z, or the other way was written in the question, c to the power 1 over n is equal to w, where our z is 1 plus I. Okay. So, and our n is, our n was what? 3. So, because of this, okay, yeah. So, because of this, okay, all we can say is that right now we are come to relate the two of them together. Okay, we are come to relate the two of them together. So we have the root of power n is equal to z, and then we are come to find the nth root, okay, of where n is 3. So we are come to find the nth root, okay, of the complex number. So first of all, we know this is w, okay, and we can express z in terms of its how do you call it, modulus. So let's express z in terms of in the exponential form, okay. So magnitude of z e exponent theta I, okay. But what is this theta? So this theta is called the argument, okay. So we already talked about argument, and in particular the principal argument. So what's an argument? An argument is just, how do you call it, the angle it makes with the real axis, okay. The angle a complex number makes with the real axis, that's the principal argument, okay. So let me write re. And so what's the argument means that now with this angle, if you are going to add 2 pi, or if you are going to add 180 degrees to the angle, okay, if we are able to add 2 pi 180, we get back the same angle, okay. So argument is not only the principal argument. The principal argument is the initial angle. So the argument, okay, the normal arguments, okay. So principal arguments normally has a capital ARG, but the other argument is they normally use small a. So the argument of a complex number, okay, when you have a small letter, is the principal argument. We find it how we normally find it, plus multiples of 2 pi. So I can say my argument, small arg, okay, or z, is equal to the principal argument. Or let me just do it this way. Principal argument, capital ARG, principal argument plus 2 pi k, where k is any number, okay. So you can add multiples of 2 pi, okay, multiples of 2 pi. So in this case, I'll just say where k is a real number, okay, and then k is positive, and starts from 1 to infinity. It doesn't matter where it starts from. So I hope you understand this. So an argument, if you don't understand, please say it. We are almost done. Okay, we are almost done. So an argument, the principal argument is there, and then you add multiples of 2 pi or 180 degrees to it. If you are working in radians, you do 2 pi. If you are working in degrees, you do 360. Sorry, did I say 180? I'm very sorry for this. Erase it. Okay, 360. You add 360 degrees to it. So that's how we get our argument, our normal argument. So in this is the argument. This is the argument. Okay. This is the argument. This theta is argument. So I'm going to rewrite this. Okay, so the algebra group, okay. If you are not in the algebra group, if you're not in the algebra group, I'll send you a number so that you can message to add you to the algebra group at the end of the lesson. Okay. So when I'm done with this question, I'll send it. Okay. So let me just erase this and then we continue. Finish up. We're almost done. All right. So in continuing, we are about to finish. So we have z is 1 plus I. So let's express z in its polar form. So we know that the modulus we already found it to be root 2. And then we already know that the principal argument. So you can either do capital theta or you can do capital capital ARG of Z. Okay. Or you probably like the theta. I'm sure you probably like the theta. So let me just use that one. Because this one looks long. Okay, so we have theta. And then you said it's 45 degrees. Or 2 pi. Sorry, pi on 4. Pi on 4. 45 or pi on 4. Yeah. So this is how we get our principal argument. And then the rest of the arguments are multiples of 2 pi adding to this pi on 4. Okay, so in that case, we can express z. Z is equal to, how do you call it? Z is root 2 e exponent pi on 4 plus 2 pi k I see the rep. So you can put this in brackets. So what we have here is the total argument. Okay. So k is any number. Normally k in this case, you will see where k ends. But then this is it. Okay, this is the total expression. All right. This is a total expression. So right now, okay, we will need to find z to the power 1 over n. Okay. So basically, z to the power 1 over n will just be this raised to the power 1 over n. Okay. And let me rewrite that at the side here. Let me raise this. Let me raise this, sorry. I'll put the 1 over n back. We have 1 over n. So when we are doing this, we just get, so we have root 2 to the power, so n is 3, right? So we just put 3 there. So root 2 to the power 1 over 3, okay? That's our first part, times. So root 2 to the power 1 over 3. I hope you can all hear me. Can you all hear me? Can you hear me? Okay, someone is asking why is it plus 2 pi to the argument? So when you add 360 degrees to an angle, you get the same angle, okay? It's not the same angle you get the same position, okay? You get the same position back. It's like you've gone around the full circle, okay? So when you go around the full circle, you come back to your original position. So that's why we have a principal argument. That's our starting position. And then we go around the full circle, that's 2 pi. So if you're adding multiples of 2 pi to it, that means that you're going around in full circles number of times, okay? So right now we have 2 pi, square root of 2 to the power 1/3. And then we have e exponent, the principal, the argument, okay? That is, let me just call it a. Sorry, theta. Okay, let me just call it theta. I, okay. That one too is also raised to the power 1/3. So we can, so if to the power 1 over 3. So if you have e exponent a to the power b, okay, we just multiply, okay, so it's become e exponent ab, right? I hope you all get it. So let me raise this. I hope you all get this. Can you hear me? If you can hear me, if you can't hear me, please tell me. Okay, so we have this. So if I erase this and then I type the other one, so it becomes root 2 to the power 1 over 3, okay? E to the power theta over 3I. Okay. Now you can just see that that was just a simple substitution that we did. Okay, it wasn't anything complicated. Yeah, I'm writing on plenty sides of the board. So please, do you understand this part? So I just divided the power of E by 3. Okay. So in the end, okay, let me erase everything. I hope you've gotten it noted down. Okay, let me erase this part. In the end, so I'm closing with this, and then I'll send the number for the algebra group. Okay. So in the end, we get our z is equal to square root of 2 to the power 1 over 3. Okay. E to the power, now we have to write the full argument. So the principal argument is pi is 45 degrees, or in radians pi over 4. So I'll just write pi over 4, okay, plus 2 pi q, okay, multiplying with 1 over 3, okay, and then obviously our I is there. And so if we simplify, we'll get 2 to the power, this is 1 over 5. I hope you know why it's 1 over 5. 1 over 6. So 2 exponents, 1 over 2 times 1 over 3, and that's 1 over 6. Okay. Because we are multiplying the fractions. 2 to the power 1 over 2 first times 1 over 3. That's 2 to the power 1 over 6. I hope you understand that. Okay. And then for the continuation, we have e exponent. Now pi over 4 times 1 over 3 is what? Pi over 12 plus 2 over 3 pi k I. So all this, so this is the solution for this is not z, sorry, this is w. Why did I write z? Okay. Our roots, okay. And because, how many roots do we expect? Because it's cube roots, we expect 3 roots. Okay, so our k is equal to 0, 1, 2. So it is, you don't add a 3 because you repeat what you were doing again. Okay, so 0, 1, 2, because we expect 3 roots. Okay, so our k starts from 0, 0, 1, and 2. So I hope you understand this part. Okay, so you can decide to simplify, okay, and write down the k. So if let me erase the top part. Let me erase the top part. So yeah, if I'm writing it here, each of the expressions is going to be so 2 to the power 1 over 6. So this is our first one. E to the power pi on 12. That's when k is 0. To the power 1 over 6 e to the power. So pi on 12 plus 2 over 3 pi. If you use your calculator, okay, we are going to get 1 over 12 plus 2 over 3. You get 0.7. 3 over 4. Yeah, I'm not using a calculator. Pi I. And then that's when k is 1. And then when k is 2, you can do the last one. I don't have a calculator on me. So yeah, I hope you understand this one. This is basically complex numbers in a nutshell. there are more stuff when you solve more questions. So this like just a recap, okay, for those who are home and they want to like know what we've been doing during the tutorials. Okay, so this is the complex number parts. We obviously did some parts before, and we want to continue. We want to go to vectors. Okay, so the next thing we are doing is vectors. Okay, vectors and matrices. So I want you to revise like what you've done in the complex numbers. Those who are in school, you already know this. I'm sure you are done with this, and then you want to move on to vectors. So yes, so we'll move on to vectors next time. Sorry for all the glitches. Okay, tell your friends these glitches don't happen. Today is the first day, so we're just seeing how and what were were was going wrong. Don't get us wrong. We put a lot of preparation into it, so we will see the results very soon. Okay, so just have a little bit of patience for us. And so let me put in the chat the number that you should dial if you are. Someone said we didn't finish complex logarithms. Don't worry. I'll just cover it shortly before we move on to vectors. Okay, it's not anything hard. It's what we've been doing. It's what we've been doing all along. Okay, so at this point, I'm going to type in the number that we'll be using. So text this number if you want to join the algebra group. Okay, if you want to join the algebra group. I'm getting the number. Okay, so text this number if you want to be part of the algebra group. 027544079. So the name is Otabo. I'm texting it in the chat. So you text. You text this, okay, this number 02754444079, and we'll add it to the algebra group. So just text that you want to be added to the algebra group, and we add you. Okay. So thank you very much for your time. Okay, thank you very much for your time. This meeting, I would say, had a lot of challenges. I would say, but then in our next meetings, there'll be little to no challenges. So just get prepared, get yourself ready. I hope right now you know that there are online tutorials. So from anywhere you are, from Accra, wherever you are, you can still access the Gesa tutorials. Okay, thank you very much for your time again. So right now, we can now leave. Okay, so.